Okay, so hello and welcome to the first talk of today. It will be about, in general, a little bit of asynchronous programming and a little bit of not, and it's a mix of various topics, so I hope you'll enjoy most of them, if not all. So the talk is Need for Async, Hot Pursuit for Scalable Apps. So even though the topics are very, weird and not very similar to one another, the similarity lies within all being something that you can use and should use if you need a scalable application. And maybe you don't use it directly, but maybe you should at least know that it exists. So my name is Konrad Malawski. I work at TypeSafe on the AK team and also did a little bit of reactive streams work recently. Random stuff. What I do otherwise. So I run a Geekon conference. It's in Poland in May if you want to visit Krakow, wonderful place. And also was involved in a bunch of other community things, so including the Polish Java user group, software craftsmanship, and the Lambda Lounge, and the Java 1 program committee for the emerging languages track. So I tried to smuggle in Scala to Java 1. That's basically my role there. So credentials, I did a little bit of the TCK, but enough about me and more about you guys. So I need to know a little bit, if you at least know what reactive programming is, like hands up. Okay, and who knows what akka is? Okay, great. Who's actually using akka? Oh, less people. Okay, but you're aware of it. That's fine. There won't be too much akka in this talk, but there will be a lot of talk that akka is using. So maybe you'll find it enjoyable this way. So the way I got to do this talk is I figured, well, we have this great stuff, but let's actually explain what's underneath all this stuff so we can appreciate it. And a great quote from Martin Thompson that explains these concepts for me was that high performance is not really about bit twiddling and changing one line or two lines to do a bit operation instead of adding a one, something like that. It's more about the core and fundamental design principles that something is built with, right? So if the algorithm is crap, you can do all the kinds of bit fiddling you want. It still will be slow if the high-level algorithm is, n squared or something. So, agenda for today. Loads of topics, and there's even a bonus section. And we'll see how far we get. And feel free to interrupt me if you want to. But yeah. Let's go. So why this talk? Because the free lunch is over. So this quote is pretty old by now, but I'm still using it. So the free lunch is referring to if you add more CPUs to your program, or you add a better CPU to your machine, the program goes faster, right? But that's not what's happening in recent years. In recent years, we see more CPUs, and in order to take advantage of more CPUs, we need to make a little bit of work ourselves, or at least use tools which are ready to leverage multi-core and distributed systems. This is how we come to distributed computing and asynchronous processing in general, right? Because we want to leverage more cores, because we're getting more cores when we get just normal speed up of a single core. Nothing new, right? We've been talking about this for years. And what I want you guys to take from this talk is to not be buzzword-driven, but be well-informed when you make decisions, both about frameworks and, in general, what to use in your projects. So, basics. What's synchronous? What's asynchronous? Simplest thing on the planet is synchronous communication. So I send you a message, and I wait until I get the reply back. This is basically a method call, right? I call the method, and I wait until it returns. And then I call another method. I wait until it returns. Synchronous programming, right? Simple. So how does asynchronous change this? Well, asynchronous means I send a message. I don't wait for a reply. I send another message. And now, first thing that can happen here. The ordering, if we're fully asynchronous, is not really guaranteed, right? I can get a reply for the second message before I get a reply for the first message. Why is that nice? That's nice because maybe the second message is, invalid or very simple to fulfill, but the first one maybe takes a longer time. So instead of waiting for the long message to be computed, I can already start processing other stuff that maybe is way faster. So here, third message, I send the third message and get a second reply back for the third message. And only after all this stuff has happened, I finally get a reply back for the first thing, right? So this already changes quite a lot in terms of how we think about communication and, ordering guarantees in such a system. So let's talk about async where it matters. In this example, event loops and actor systems and anything that's basically trying to put many executors on a smaller number of resources. The same could be said about threads. When you have more threads than you have CPUs. Exactly same thing, at least concept-wise. So conceptually, let's talk about three actors. They have mailboxes. And the way an actor works is it takes messages from the mailbox and it gets CPU and works on the message. So, and the lines here signify time, right? And I will be using yellow and blue to signify which actor is using which CPU at this point in time. And like I said, if you don't want to think actors, you can think threads. Basically the same thing in this example. Not in general, but in this example, yes. So, we have two guys. Each one of them is processing a message, so we used both of the CPUs. And at the end of each processing of a message, it can decide, well, do I want to keep processing other messages, or do I give the thread to someone else? The middle guy decided, yeah, I still have messages to work on, so I will continue using the yellow CPU. But the bottom guy, it's not really blocked, but it's, doesn't get resources, so it's maybe starving. But let's go further. So at the end of each processing of a message, there's this point in time where there can be this handoff, where the bottom guy can get CPU and can start processing, at least in theory, if he's lucky, his messages. So okay, after the second message of the middle actor was processed, the bottom actor gets the CPU and now can do his job. And on the top, we see the guy keeps working on his mailbox, right? He keeps pulling in more messages. So the middle guy now is a little bit starving. And we call this starvation, right? It's not a new concept, but what I want to highlight here is the gray zone, right? So the gray zone is when I use a blocking I/O, I use a blocking database operation, a file operation, a network operation that I send the data and I wait, right? So now the bottom guy, from my perspective at least, from the program's perspective, is wasting resources because it has sent some data to the database, and instead of giving me, the middle guy, some CPU to work on it, he's just idly waiting, right? So this is a little bit of wasted time. So what can we do about it? So this is synchronous I/O, and in general, any kind of asynchronous I/O or asynchronous database driver would work like that. But I signal some data to the database, right? Bottom guy is signaling some stuff to the database thing. And then I get a callback once the data has been written or the thing has been processed, right? And it goes into the same mailbox. So we're reusing the same mechanism. And the difference is, well, now we don't have a gray area that is wasted, but in user land, we can just keep using this thread for my middle actor, right? So we're improving utilization, like actual utilization and not utilization on waiting. Okay, green zone, good. Lessons learned. That blocking is actually indistinguishable from being very slow, right? So if you look at it, if the bottom guy wouldn't be actually blocking here, but only processing this message for 5 minutes, the effect is kind of the same, right? The other guys are not getting the resources they want. So this is why we really don't like blocking, but like I said, being very slow kind of gives the same effects. So you want to chunk up your pieces of works into very small pieces, so you can, be fair to your other peers. So no parking at any time. But now let's jump topics a bit. let's talk about latency. And this is a quiz, so I require some attention and maybe hand waving from you guys. So, latency quiz. Which one is latency, yellow or blue line? Hands up if yellow. Hands up if blue. Oh, more people think it's the blue. Well, actually, sorry. Yellow is, at least when we look at the queuing theory definitions of what latency is the time from, I come to the queue and, I get serviced, right? If I'm at the border, the guy is looking at my passport, then I'm at least being serviced, and it may still take some time, but at least, the process of handling my thing has started. And the bottom thing is more usually defined as response time. And now many people are scratching their heads, isn't that the same thing? Well, that's actually the problem, that these terms are very often used interchangeably. And in, colloquial beer discussions, that's fine, maybe. But when you're discussing maybe an SLA, and people, talk about latency, and you talk about response time, make sure that you understand it's the same thing. It's fine if you define, okay, when we say latency, we actually mean response time. But it's way better to actually spell it out during a discussion than to assume that the other guy understands also the yellow or the blue as the same thing you understand it to. It's just a language thing, I would say. So what is the green thing? Any ideas? So it's referred to as service time. So service time plus latency is the entire response time, at least in these formal definitions. So if you want to be really precise, these words are the ones to use. If you want to be somewhat precise, then at least define with your discussion partner what you're talking about. So, for the rest of this talk, I will define response time as being latency. Example, right? It's good enough if we understand what we talk about. So, another quiz. So is 10 seconds latency acceptable in your applications? Maybe hands up. 10 seconds, right? That's usually maybe a batch thing or something slow. 200 milliseconds, right? Yeah, people starting to raise their hands. This sounds already pretty good. And now we start getting a little bit more fuzzy. How about most responses within 200 milliseconds? And who starts to think I'm getting somewhere like this is a trick question? Yes, this is a trick question. Okay, because the following questions are like, so mostly within 20, but some within 1 minute, right? So you see we're starting to go into the actual behavior distribution of the latencies, not only saying in an SLA it has to be 200. That's a very hard SLA. But do people die if we go beyond 200 milliseconds? If they do, then we better try to stay below 200, right? But if they don't, and I don't know, someone will be a little bit frustrated because the kitten picture is still loading, then maybe it's fine and we don't need to spend 4 weeks trying to optimize the kitten service, right? So it's a trade-off. We can always go faster, we can always slap more caches or more machines or better algorithms on stuff, but do we need to? It's a good question to ask yourself sometimes. So, and this is actually, again, from Gil Tennis' talk. These questions are actually stolen from the How to Not Measure Latency talk. Highly recommended. So the thing that we actually want our SLAs to look like is, okay, so 90% of the requests should be below 200, and 99 below a second, and we really shouldn't go beyond 2 seconds for a response, right? And sometimes people, instead of talking about this distribution, so like I displayed here with these percentiles, they talk about our response time is 200 milliseconds on average, and then they remember a little bit of math from university and see, okay, standard deviation is 60, so let's derive, percentiles from it. So, because, bell curve, and I move a little bit to the right, and this is my latency. Turns out that's not how reality works. So the mathematical model works really fine, at least the simple one, if it is a normal distribution. But turns out the profile of latency in applications is very rarely normally distributed. It's very messy and chaotic. So remember that, and don't directly derive percentile values from, mean and average and standard deviation, right? Instead, measure everything that you can, and there's tools that help you do that. For example, HDR histogram is a histogram implementation by Giltana, and what it allows you, the screenshot is from the JHiccups library. It allows you to record basically pauses in your JVM, and then you can draw it out, like on the bottom picture. And when you compare these pictures, it's the same system. But on the top system, you only see, on the top picture, you only see, okay, there was this hiccup, and it took, how much is it here? Okay, 100 milliseconds, and it's sometimes happening. Okay, but on the bottom picture, you see the distribution of how often it's happening, right? You can see, okay, this system is exhibiting certain modes of operation, right? This number of requests is having this behavior, and then it's slowly getting worse, and then suddenly it's going worse really fast. So what we have to do then is to investigate and look at this graph, maybe with a little bit of imagination, and try to figure out why this could be. Why does this system have these three modes of operation? And then you need to pattern match with something that you remember maybe from your project or childhood. In this case, looks a little bit like a snake. But actually, then you remember, it's actually an elephant. So what I mean with the elephant is, you remember in your system, we have this queue, right? But this queue, it has these buffer sizes. All right, so maybe the queue here, it's growing and still coping, but maybe here it's completely full and starts rejecting work, and we need to resubmit or something like that. You can track these behavior kind of hints to actual, code internal knowledge that you have about the system. So that's the elephant. You look at it from the outside, it's a snake, doesn't really make sense, but the elephant is the thing that you can connect to that actually makes the graph make sense. It's the thing inside that causes this. So the right-hand side of such graphs we usually refer to as tail latency. So it's the higher percentiles, right? And these are usually the ones we want to optimize, because no one really cares about the 50% case. Usually we talk about the 99 or 99.999 percentiles, right? So that's the tail latencies. Something you can Google for afterwards. So, lesson learned in this section: use precise language, or at least define what you mean by the words you say, especially when you talk about SLAs and try to get to an agreement with someone. And verify the results and try to think about the graphs. Don't only draw graphs, but also try to understand them. Okay, topic change again. So like I said, we're gonna jump in between topics quite a lot. So concurrent and lock-free and wait-free algorithms. So maybe going from the beginning, you know what a concurrent data structure is? Right, everybody should know that. A lock-free data structure and a wait-free. Yeah, the usual slowly going down with hands, which is fine. So concurrent data structures are most easily defined as if multiple threads access the data structure, it doesn't blow up. That's a non-formal definition, but very intuitive. But let's look at what can happen in such a data structure. So you have two threads, or multiple threads, and they try to write a value into some container. So in this case, A tries to write, B tries to write, B wins. And again, we have this loop of people trying to write the value, and somehow always the other guy wins. So what does that mean? So A keeps retrying, right? And these other guys also write the value, but they always win. So moral from this story is A is a complete loser. But more formally speaking, it may never make progress. By making progress, here we would define it as actually setting the value or stopping to even try, right? Some form of progress. Another thing that can happen in a concurrent data structure, which is also perfectly fine, is A tries to take a lock. The other guys write the values. And A is still waiting because it's waiting on the lock and no one is unlocking it. So again, same result, but slightly different actual behavior. Because here we have the first guy still waiting. In the previous thing, he would be trying again and trying again. Still concurrent data structure, still a valid concurrent data structure, but A is still a complete loser, and he still may not make progress. So this definition will be interesting for the following algorithms, but let's look at which APIs actually expose such behavior. So this is from the concurrent queue implementation in the JDK, and it has a bunch of methods which you can use to put values into the queue. One is offer, and it returns true or false. Well, it returns true if it was able to put the thing into the queue, and it returns false if it wasn't. And then you can keep retrying, right? That's the first case. Then we have add, which throws an exception if it failed to put stuff in the queue. Again, we could do the first implementation based on that. A little bit less nice because exceptions for control flow, but okay. And then the third one, which is no fun. Because put a value, and it will return a Boolean which says true or false, depending on if it was able to put. But it actually blocks until it is able to put. Rephrasing that, this method will never return false, because it will keep waiting until it can return true. And in this method, we don't have a timeout, so it will wait forever. Not a really reactive thing to do, because I would maybe try to put into the queue at most within 100 milliseconds, and there's APIs for that as well, but this one waits forever. So no fun. So concurrency does not mean parallelism, and parallelism means when multiple people keep working at the same time, and concurrency means, well, there is this structure that multiple people can try to go to it, but it will actually execute sequentially still. So slightly different terms. A concurrent data structure can be a parallel data structure. This way around, not the other. So lock-free, also sometimes referred to lockless, right? So here's a picture to explain of what I mean by lockless. And it should play. Right. So lockless means that you never really wait. So you see there are traffic signs, traffic lights, but we don't really use them for synchronization. We go as fast as we can through the traffic, and we don't really crash. So that's still fine, even the people don't crash. So great. This is a lock-free data structure. A better example, but I didn't have a nice GIF for it, is if they would actually crash, but then they back out a little bit and try to go through again, and they crash again. So they keep trying and crashing until they finally don't crash and go through the traffic. So formal definition-wise, lock-free means that if run sufficiently long, at least one of the threads will make progress. So if you imagine that traffic there, that crossing, it would guarantee that at least one car at a given point in time is able to cross. And the other ones all crash into each other. So everybody backs out and tries to cross again, but at least one will make the crossing properly, and the rest crashes and tries again. How does this look in code? Very simple. So we have for example, atomic reference. And here I'm implementing a queue that is implemented on top of this atomic reference. So I just want to add a value to the queue here. So what I do is I take the frozen value of the queue here, I append to it, and then this operation, so queue, compare and set, previously observed queue value, and updated queue value. And the semantics are, I compare whatever is inside this atomic reference with previously observed value, and I insert the new value inside. What this means, I'll explain that with a picture. First, this is actually something that CPUs implement. So this is actually an n-atomic operation on Intel chips, and it goes all the way down to the hardware. But then we retry. So if I wasn't lucky and I wasn't able to set the value that I wanted to, I will retry. So I call myself recursively here, and yeah, random Scala information. In Java, you would get a Stack Overflow exception if you do that a lot of times. But in Scala, you don't, because this is optimized away and actually compiled down as a while loop. So because Scala is a functional language, there's a lot of recursive calls, so this is a optimization the compiler does for you. So it's very nice to write these things, even if they're potentially infinite. But let's explain what happens if multiple people write to the same black box. Okay, we have these two threads, and both at the same time observe the value. They observe the gray queue. They put things out of and take things out of it, try to append to it, and issue the compare and swap. The other guy does the same, but because he was the latter to issue the compare and set, well, he doesn't make it, but he can retry, and after the retry, he's successful, and everybody is happy. And the state of the queue is here on the right-hand side then, right? Good. So wildcast. So weight-free data structures. So what's the guarantee here? The guarantee is that an algorithm, a weight-free algorithm guarantees that after a bound number of steps, we will make progress, right? So in the previous one, we still can get this infinitely retrying case. Here we don't have the infinitely retrying case. It may retry up to a given number of times. Specifics-wise, the concurrent linked queue from the JDK is a very nice implementation of that, but as you can see, not that simple. And basically, if you want to understand that one, best read a paper, and I'm not doing a talk specifically about that one, and it would be a topic about specifically that algorithm for a 1 hour or even more talk. So this is more for your information. But lesson learned is there's different ways to implement a data structure, and sometimes you need to implement one yourself, but sometimes you're simply picking the right tool, right? And it's good to know that there's these different ways to implement a data structure, and if you actually know that you need a concurrent one, well, how parallel should it be? How should it be spinning and trying to do the right, or should it, bail out as fast as it can? So, good to know. Let's talk about I/O now. So, different topic again. So, I/O stands for not the Google conference. That's also fun, but not that one. It's input-output. And then we have AIO, which is the asynchronous input-output, at least on Linux. And then we have NIO. That's in Java, right? We also have 0. So 0 is a little bit tricky here, but it's part of AIO. But you'll see next. So that's a fun quote from my colleague TypeSafe, who was working with us for quite some time, Havoc. So he was working on a lot of GNOME and desktop stuff, right? And what people do there, they have an event loop, right? So when he came into Java land, he was really surprised, like, where the hell is my event loop? Let's talk about it. And actually, interruption. So interruptions are something that drives most of syscalls and basically how computers work underneath. So this is a good example, good place and time to talk about them. So we have these two modes in the CPU. Do people know about user space and kernel space? Right, everyone knows. So I'm going to go fast through that. So the only thing you should remember, or maybe remind yourself, is that this is an actual CPU mode. It changes how the CPU is addressing memory. And going from one mode to the other actually takes time. I don't have very recent data, but it's at least hundreds of cycles, even on new CPUs. And on a Pentium 4, it was thousands, which was almost a millisecond, right? Well, half. On newer ones, I'm sure there's someone who could give me a number, then I can update the slide. But it's still pretty painful. Why is it painful? So, because when we try to read something from a file, what we actually do is we tell the kernel, hey, I want to read something from a file. So we do the mode switch, the syscall is done in the kernel space, and when we go back into user space, my application gets the data, and then I can issue a write of the same data. This is if I would implement a very naive copying algorithm. Right? I copy a file by going through the JVM. Not optimal, but let's think about this here. So we have 4 mode switches. That already accumulates to some wasted time on the mode switches. But yeah, it only gets worse when you start thinking about the buffer spaces. So what I mean by buffer spaces here is when the kernel reads data, it reads into a kernel buffer, and when it hands it out to the user, to my application, it needs to copy it into a user space buffer. So we have one useless copy kind of already, and then we have another copy from user space to kernel space because we are writing this maybe to TCP or somewhere. So we're using a lot of copying here. And also, we are blocking all these operations while the kernel is working in the kernel here, in the kernel space here. Userland is doing nothing, right? We call this IO wait. So one improvement to that is the synchronous IO. And yeah, in Java it's NIO, which no one calls new anymore because it's in since 2004, but that was originally the name. But what it exposes is APIs like that. I want to perform the read, and I stay in my user space thread. I can keep doing other stuff, and I will get notified once the read has been performed, and I will get this data asynchronously. So we're not wasting time in user mode here. Just once it's done, I'll get a notification. Same for the writes. But we're not really changing the number of copying that is happening in the background, right? There's still the same number of buffers which the data goes through. So let's try to do something smarter instead of working harder. And this is what the Linux and kernel people in general figured as well. And this is what we call zero copy, even though technically it's not zero, but you'll see that in a moment. It's a kernel a function called sendFile, because this is the actual most popular use case of this API. So imagine I am a web server, and I'm a web server that is serving static content, cat images, right? So I want to be really fast at serving the cat images, so I want to avoid copying the data around, because it's wasteful and takes time. So what sendFile does, well, yeah, it is a blocking operation, as you can see here, but it does not do any copying. Instead of, well, it reads from the disk, for example, and then it pipes directly to the target without going through user space, right? So this is really fast for stuff where we don't need to inspect the data, right? Because user space never really gets the data, so it's fast because we avoid the copying. Cool. That was my first reaction when I saw it. Oh, this is amazing. And this is basically what all the super fast static content file servers use, right? Basically, everything is built around sendFile. Now you know. So that's an interesting topic to talk about as well. So will asynchronous I/O beat synchronous I/O? Because sometimes people refer to asynchronous being infinitely faster, and I'm certainly one of those guys who should be saying that, but I'm not, because that's not always the case, and even rarely the case. What asynchronicity gives you is better scalability, and also sometimes performance, but that's not really the focus. And also, disks are really good as sequential reads. A disk is really good to go to a sector and read the entire sector, right? So synchronous I/O, maybe you actually want synchronous I/O because it's good at reading synchronously a sector and just keep spinning there. Okay, another topic. So the C10K problem. And now we're jumping a little bit from the from files and disks to network. So who is familiar with the C10K problem? Not that many. Okay. So it's not that new actually. And C10K stands for 10,000 concurrent connections. And by not that new, I mean, 12, maybe 13 years ago or something like that. And the problem initially was stated because of Apache HTTPD and problems with scaling it to a very high number of concurrent connections. The problem still exists with any kind of web server that is using thread per request, right? Because there we are limited by the sheer amount of how many threads we need to keep running, and then the scheduling overhead and the multiplexing of these threads just starts to be such a baggage that we cannot scale to so many concurrent connections. So like I said, the problem was originally stated because HTTPD using the same model as Tomcat and servlet containers, which is thread per request, and having trouble to scale it to more connections. So important thing, I said it a little bit, I signaled the problem a little bit already, but this is orthogonal to performance. The problem is strictly about being able to scale out on this single node, to make it take more connections. It's not really talking about any kind of performance here. They are related somewhat, but we can optimize for one or the other. Okay. So how were servers implemented mostly back in the day, and maybe still some implementations using that? So first the select and poll methods. And here we're talking about selecting. I have a number of sockets. So I have a number of clients using my API, for example, my server. And they keep their connections open. And I need to figure out, okay, who has data to read or write, right? So the clients are sending me data, but only 5 of the 5,000 ones are sending me data. So I need to select which one I will read from. So this is this array. And then the kernel exposes methods like, okay, poll and tell me which of these are ready to be read from. This is basically what we mean here. And it has a timeout. So if no one is ready to read within 100 milliseconds, then we basically return with an empty array here. So we poll. And then here's the problem in the scalability of this part here. So because the return type is an array that we need to scan and ask every of these connections, well, do you have any events for me? Right? So we're doing the scanning manually here. The solution to that part of the C10K problem was to instead create a new syscall. The new syscall is called epoll. And sadly, it's not a cross-platform. So Linux has epoll, Windows has something that I forgot, and Macs have KQ, I believe. But they all do the same thing, the only problem being it's different APIs. So once you go direct to epoll and you're not on the JVM, you would need to implement it 3 times. So what it does is I create a flag, which I will use for reading basically I register that I'm watching for the sockets, and then the kernel knows, okay, you're interested in these sockets, and then I do a similar thing as previously, but I pass in an array, a pre-allocated array. This is C-land, right? So remember good old C days of passing in an array. And then the kernel, what it does, instead of giving me back an array of all the sockets all the time, it populates the one I gave it with starting from exactly the sockets that have data available. So I'm not needlessly scanning over sockets which don't have data available, right? There's less scanning involved, so that's way faster to select the socket. And then we do it again and again. So what this teaches us is that ON is a no-go for epic scalability. And what do I mean by that? I mean by that things that are really at the bottom of our both operating systems and your random application, like any application, if something is really at the bottom of all the cores, it should be fast, because it's worth to optimize the thing that everybody is using. Well, everybody is using scheduling because we use threads. Everybody is using socket selection because we write HTTP servers. So these things really need to be O1 to be really scalable. So it is a go for epic scalability. And the same lesson can be for our applications, right? So let's talk about distributed systems. Random topic change again. But what is a distributed system actually? My favorite definition by Leslie Lamptort is it's a system in which failure of a computer you didn't even know existed can render your own computer unusable. And when you think about it, it sounds as a joke, but it's actually a wonderful formal definition because I can check that. For example, I have a database server and I have a web server, and some customer is coming to my web server to order a thing. Database goes down. Does the user know that I have a database? No. And does he care? No. But it rendered his system unusable because he can't do anything with the system now. And also, the bigger the system, the more weird behavior it exposes. Right? I'm sure you've seen that once you get more machines, at some point one of the machines will get a bad disk or start behaving weirdly. So instead of hiding this problem, we need to embrace it. So let's talk about optimizing the long tail latencies. We know what the long tail is, and we'll be doing that by issuing duplicated work. So yeah, I will increase the load on my cluster, trading it off for better latencies, better response times. Okay, the technique goes like this. It's called backup requests, and here I have an actor that has an SLA of 300 milliseconds to give a reply to some question. It gets the question, and it knows there's 3 actors in the system, maybe on different nodes, right? Which I can ask this question, and they should know the answer to it. You can imagine this being a distributed cache, something like that. So, and at the bottom, here's the timer of SLA and my time spent doing stuff already. So, first I send the question to this one guy because I know, okay, he has the data and I'm asking for it. And at the same time, I start the timer for a fraction of my SLA. So my SLA is 300, so I start the timer for 100 milliseconds. And once the timer runs out and I didn't get a reply yet, I start panicking and running around the office asking everyone else to give me the answer, right? So we do exactly the same in distributed systems, and we start panicking and asking the other replicas to give me the data. And then turns out, well, actually the second node was faster to give me the reply than the first one. Why? Well, maybe the first one is being hammered by all the other servers because everybody has it on, well, first try this node. If it's a naive implementation, and then it's under heavy load all the time. But the second node is not really under that heavy load, so it's faster to give us a reply. So, and yeah, in a naive implementation, we would get duplicated replies back, right? I asked 2 people, so 2 people give me a reply independently. There's ways to optimize that away, so the replicas would tell one another that they have already replied, but that's a optimization. But the interesting thing here is we have both optimized tail latencies and we have fixed for the case when the upper node would be actually down if it crashed, right? Because maybe we didn't yet realize that the node is down, so by using this backup request we are actually also safe against failure. We're more resilient. So where does this technique come from? It's actually coming from Jeff Dean's blog and talk about the big table system. So also not very new, but popular and used in loads of database systems. So Cassandra does this stuff by default. Forgot the name, how they call it, but it's on by default. And any kind of cache, very easy to implement. So, do we have it in Akka? Yeah, of course. It's a router. In our world, you can give a router a number of actors, and it will do exactly that protocol. So if it doesn't get a reply very fast, it starts asking other people. And yeah, the thing I wanted to highlight is the change in actual latency distribution. So the 99.9 percentile without backup requests, that's a second. With backup requests after 10 milliseconds, we're down to 50 already. And you can see even if we back out and make it after 50, we still have improved the 99th percentile a lot, right? This is not a second. This is still hundreds of milliseconds range, right? So is it worth it? Definitely. So lessons learned, we increase load but get better latencies. Okay, but I had an example of the opposite. So the opposite is that I have a one downstream, and I get a lot of questions. And instead of sending all questions through one by one, I keep accumulating into a bigger question, and I send one bigger question downstream. Then I get one reply back, and from that one reply, I can, fan out the response to the clients. So this is increasing latency because there's this time where I collect the data, but it's decreasing load on the downstream because it's getting less questions per second. And if it's something like a search engine and maybe the searches are the same, then it doesn't really need to do anything more because it's the same question, right? If 5 people search for cats, I only need to search for cats once and then reply to all of them with the same answer. Sorry, I missed the slide for it. So, next topic, parallelism and pipelining. So this is something best explained using pancakes. Let me explain how I mean that. So when you make pancakes, turns out different people make pancakes very differently. And we had this discussion in the team, who does pancakes in what style. And I think, was it Patrick? I think Patrick uses 2 frying pans. No, that's Roland's technique. He uses 2 frying pans, but sequentially in the manner of I take the scoop of butter, I put it on the first frying pan, and once one side of the pancake is ready, he flips it over to the second frying pan. Right? This we call pipelining. Okay, so this means that I have this buffer of scoops of butter. I put them onto the frying pan as fast as this frying pan allows me to, and from it, I have a separate buffer here to make it even more rate detached. So if the second frying pan is full, there's still a pancake there, I can give the almost done pancake onto a plate, and it's waiting there. And if the frying pan is empty, I take from the buffer, from the plate, onto the frying pan again. What this allows us to do is basically detach the speeds of processing on each frying pan. And you can imagine this being a stream processing pipeline, and one of the stages being slow, one of the stages being fast. By introducing buffers between them, they can go at independent speeds, because even if the frying pan is full, I can put on the buffer and it will consume from the buffer at its own speed. Okay, and then we get pancakes out, which I have wonderfully illustrated as these things. Yeah. So API-wise, very simple. Basically, this is Akka streams, but you don't really need to know anything about Akka streams to understand this. So it's a flow from scoop of batter to half-cooked pancake, and that's how it looks. It maps batter to a pancake. Then we have a second frying pan, which from half-cooked pancake goes to real pancake. And then, how do we connect this to a chef? So a scoop of batter to a pancake is to connect these two, right? So a flow of scoop of butter via first frying pan, via second frying pan, which gives me what I want. And these work exactly as I explained. There's buffers between them, and they can go at detached speeds, rate detached speeds. But let's talk about Patrick's method for doing pancakes. So it turns out Patrick was really confused why Roland is doing pancakes in this way. It's suboptimal. Then Roland said, well, because I have different temperatures on the different frying pans and I like it better. Okay, but Patrick's method is optimized for speed because he has more than one child. Is it 2 or 3? And he needs to really get these pancakes out the door really fast because the kids are waiting. So the API is the same. It's a flow of scoop of butter to a pancake. But the implementation is a fan-out, fan-in operation. So he takes a scoop of butter, puts it on the first available frying pan, and then bakes until completion, right? On this one, having to turn the pancake once, right? But you can see the two frying pans are in parallel working on a complete process of making the pancake. So API-wise, I just want to show that this is how it looks here. So we have a dispatch batter. It goes through a frying pan, and it merges the pancakes because we have one outgoing stream of pancake and not two outgoing streams of pancakes. Yeah. Or simply you can use a built-in operator which does that. For us in Akka streams, it's called map async. And if you have a frying pan that returns a future of pancake, you can use that. But yeah. So we do have 11 minutes, 10 minutes, and I do have another example which I can show you guys if you want to see how buffering works end-to-end. So from an application layer to the actual TCP buffers, and that's a demo. Do you want to see a demo? Yes, I thought so. So we're not wrapping up. But bonus, streaming APIs. So let's imagine I have this stream processing framework toolkit, which is Akka Streams. And Akka Streams is the foundation for Akka HTTP. It's our HTTP both server, so you could think of it, it's a jetty. It's an actual implementation of a HTTP server. But at the same time, it's also the routing layer. So it's the way you route the requests to whoever replies to them. The interesting bit about Akka HTTP and Streams is that it has back pressure built in. And you'll see what back pressure is in a second. Because we focused on the reactive streams protocol, which we have, we as TypeSafe and Red Hat and Pivotal, we have created over the last year, and now it's up for inclusion in JDK 9. So you can check the reactive streams protocol for that. And the thing it does, it allows us to have this asynchronous system, but if the downstream is slower than the upstream, we are able to communicate that it can't keep up and slow down appropriately. This is a non-trivial thing to do in an asynchronous system. You need to get some information back from the downstream to the upstream, right? It cannot just guess how fast the guy downstream is. So, this is how it looks underneath the reactive streams protocols. This is not really something you're meant to implement. It's a very low-level thing. But libraries like RxJava, Akka, and Reactor, they all sit on top of these APIs. So we can interoperate with different implementations using these. And this is JEP 266, which is up for inclusion in JDK 9 soon, I hope. So you did see a little bit of Akka streams already, but let's talk about buffers, turtles, buffers. So we have this source of tweets. Let's imagine I'm Twitter, and Twitter has this nice API where you can stream all the tweets for a given hashtag, or all the tweets on the planet. And I am this server which does that, and I'm streaming out the data, and eventually it lands on TCP because it's using a HTTP connection, right? And then the operating system needs to put it on the wire, right? So once we put it on the wire, it's out there in the wild, and yeah, TCP takes care of retransmission and stuff. So the way this works, the downstream is signaling demand until it's, while it's still able to process data. And we send data, so we generate new tweets while we can, right? In my example, I have a random tweet generator, so I just invent tweets as fast as I can. And what I want to show you guys here is that if the client is using a cell phone and he goes into a tunnel, so he stops reading from the connection, right? Because now he's in a tunnel, he doesn't have reception, he can't read from the TCP connection. Then first what will happen is our send buffer on the operating system level will fill up. Then the intermediate, this is, so this line here means where the JVM starts, right? This is a TCP implementation that we did. So then our buffer will start getting full on the TCP side, and then the intermediate tweet buffers will get full, and then the source will notice, well, okay, if everybody has full buffers, there's no reason for me to keep generating tweets, and it will stop doing that. So using this information, we can do very interesting stuff. For example, start dropping data, start sampling data, and suddenly backpressure is a first-class citizen in an API. Is that good enough? I hope so. So without talking too much about the API, you can just read the docs. Let's talk about this case. So the way Akka HTTP works, here I start the HTTP server, one line, and I give it roots, and the roots are tweet roots. And tweet roots means I will match anything that's on the path tweets. That is a GET request, and I will complete this request using a source of tweet. And because we have this pre-JSON support, it handles the marshalling of the tweet into a JSON automatically, and it also handles stuff like if you want to return it as an array, we can do that. If you want to return the stream of tweets new line separated, so every tweet JSON object is in a new line. This is how many APIs work nowadays. We can do that, and you just configure it. So we return this stream of tweets, and that's all we need to actually see for the demo to be interesting enough, I think. Okay, so on the right-hand side here, I have netstat running. Do you see netstat? Yeah. So netstat is a tool that allows you to inspect all kinds of information about the networking infrastructure in the operating system. And I'm going to run the server. Okay, server is online at localhost 80. Okay, and first I'm going to explain what I'm about to do so you can notice it, because some of the things will happen pretty fast. So I will curl the tweets API. It will start sending me tweets. Then I will simulate going into a tunnel. I will do that by Control-Z-ing the curl app, right? This means putting to sleep, not killing it, because killing it would kill the connection, right? I'm just putting it to sleep. And then on the right-hand side, netstat will see two connections open, because both the server and the client are on the same host here, so there will be two connections, right? And we will see buffers for both of them. One for the, I can start that already. So we see the tweets are streaming, and the bottom here, this is, always get those wrong, I'm not sure which one is which. I think that's the receive buffer, no, that's the send buffer, right? So here we have the send buffer, this column, and here we have the receive buffer. And once I stop this guy, first the send buffer of the server will get full. Okay. Boom. Okay. Also, first the receive buffer of the operating system of the client running curl would start to buffer, which was this guy. Then the buffer is full, so the server gets communicated with, and he knows, okay, I cannot send more data now, so I will start buffering. So that's the send buffer. And then once that is full, our pipelines get backpressured and the server stops generating data. Why is that interesting? Because we don't do useless work, right? Why would I grind my CPU if the guy can't read the data, right? So if I resume it now, you can see first it drains its own buffer, and then emitting the tweet starts again. Okay. So this is pretty interesting for any kind of streaming APIs, or any kind of, the opposite works as well, right? If you have clients uploading very big files, PDFs, movies, same thing. We can backpressure them to not go faster than we can read the data. So this is exciting because it means bounded memory stream processing. For me, that's exciting because I can actually look at the code and know how many clients I can survive. There will not be buffering until out of memory, right? in some servers, in this situation, the server would keep buffering in memory and eventually blow up. Here, we have this information and we don't even generate the data, so we stay within a known size of the heap. So that's all I got last minute, so I will show some links if you want to look at some links. Wrapping up, the talk was mostly about various techniques, but you don't often need to implement them yourself. It's very often to pick the right tool, so now you know how you can find the right tool. A lot of links, I want to highlight two of them specifically, from C++conf, Herb Sutter's log-free programming. If you want to learn more about it, it's 3 or 4 hours of very nicely explained log-free algorithms. And then the C10M problem, which is interesting but not very applicative for our work because it's 10 million connections on a single host. The talk is mostly about how one has to not use the kernel if one has to go so fast. And random thanks for many people who helped me prepare this presentation. Other talks around our stack, Back to Basics by Victor in room 8, and Without Resilience Nothing Else Matters by Jonas, CTO and founder at room 5. Thank you very much, and yeah, grab me for questions, maybe just here. Thank you.